Who knows what is lazy evaluation? Who knows what it is? So, lazy evaluation, yes, Igoduk actually is pretty close. It's basically is when expression is evaluated when it's actually needed. What is that supposed to mean? Let's take a look at lazy evaluation a little bit closer. So today I'm gonna use TypeScript for all of my explanations, because I found that things like JavaScript are quite easier to understand for younger developers, because that's what they work with. And since JavaScript has like more or less functional programming capabilities, it's kind of easy to explain functional programming, pure functional programming, using that language. But I'm not going to use JavaScript. I'm going to use TypeScript for the reasons that will be clear a little bit later. Well, the main reason is that while working with my examples, it will be quite easy to make a mistake of passing a wrong value, and all of my examples may fall apart because of that, and I will spend a lot of time troubleshooting them. So we can utilize the type system of TypeScript to help us a little bit. And I would like to make a small disclaimer saying that I do not recommend developing software in JavaScript or TypeScript in the fashion that I'm going to show today, because I'm not a professional JavaScript developer and I don't even know performance implications that this approach may have in that specific language. If you want to have like a proper lazy evaluation, I would recommend using languages that support something like that, or at least libraries that were developed by people who know what they're doing. So everything I'm going to show today is purely for educational purpose, just to show you the idea how lazy evaluation looks like, especially in languages like Haskell. In Haskell, you may hear, if you heard a little bit about Haskell, you probably know that everything in Haskell is lazy. The entire language is lazy, and today we're going to explore what is that supposed to mean. Okay, here we go. Let's go to our folder where we keep all of our projects, and let's create a project called lazy. So TypeScript is a superset of a JavaScript that was developed by Microsoft. And you can find the implementation here, but we're not going to use this TypeScript today, because setting up TypeScript is kind of tiring and kind of cumbersome in some way, because you have to install it through npm and stuff like that. You have to set up the project. I'm going to go a way easier route today. How many of you heard, well, I mean, my chat probably heard about it, about a thing called Deno, or Dino. I think it's supposed to be pronounced like Dino. Yes, this one. It's a secure runtime for JavaScript and TypeScript. Basically, it's like Node.js, but with TypeScript. And the cool feature of this particular thing is going to be clear once we download it. Let's actually go ahead and download it. Of course, they are suggesting to use their shell script. I mean, come on, like, I don't even understand why you need to do that. Like let's just download the latest release and everything is going to be clear. Seriously, like, I don't understand why you need all of these shell scripts and stuff like that. I just don't understand that. Like, oh, let's open releases, the latest releases. And we have Linux x64. Let's download this thing and let's actually put it somewhere here. Yeah, I think it's good enough. Think it's good enough. And look at that. Take a closer look at this file. Do you notice anything weird? It's not tgz and not tar.gz. It's not a tarball. It is not a tarball. Let's unzip it. Okay, 57 megabyte. What the hell is this file? ELF 64-bit LSB shared object. It's executable. A single executable. The whole interpreter. Why Node.js is not that? Why do we need all of this weird different structure? Why Node.js is not that? I don't understand. Like, something went horribly wrong when we started to go into web development. Like, something went horribly wrong. I guess. Yeah. Here it is. And on top of that, it supports static typing because it's not using JavaScript by default, it's using TypeScript, and this is the thing that we're going to use today. So it showed some kind of an error before. I didn't even know what it showed there. Main panicked, unwrap error, valid to blah blah blah. I think I tried to evaluate it in a weird environment. I think I tried to run it like that. It panicked for the first time with a Rust error. If it compiles, it works, am I right? Anyway, so let's go into... yeah, another interesting thing, instead of like C, C++, they're using Rust. So yeah, this is sort of main selling point of this thing. They're single executable, they're using TypeScript instead of JavaScript, and they're using Rust. And I don't know exactly what happened there, but if it compiles, it works. Let's create a lazy.ts file and let's start exploring. What Emacs is telling me something. So couldn't locate project root folder with tsconfig.json. This is probably my Emacs extension trying to run TypeScript server or something like that. Let's ignore it for now. Let's not listen to it. Okay, so let's actually take a look at a very simple function that takes two numbers. This is TypeScript, by the way. It's just like JavaScript, but with types. That's why it's probably called TypeScript. All right, and now we should be able to do something like that. Boom. It compiled it, and it didn't print anything because we never actually called this function. Excuse me. Console log sum 10, 20, and there we go. There you go. Here's our sum. But this sum is written in how some people will say very eager style. It is in a very eager style. So basically, if I add 5 here, the end result is going to be 35. But the most important part here is going to be that this sum will be executed before we go inside of this function, right? In lazy evaluated language, that sum is not going to be evaluated until it's needed. It's not going to be evaluated until it's needed. So, and it's going to be evaluated only inside of this function. How can you achieve that? How do you generally postpone execution or any kind of computation in any language? How do you postpone execution? So you have some code, but you don't want to execute it, you want to postpone it. Well, somebody actually was extremely close. You wrap all of that in the functions. So now these values are not executed until you actually ask them to execute. So let's actually create like a separate function. Let's call it a lazy sum. And the lazy sum is going to actually take things like that. So you see every value is lazy now. And so to extract the values from A and B, you have to call them. And then if you run it like that, it will fail with a compilation error because I forgot to wrap it with another function, because you see this is also a function. And this is exactly the reason why I'm using TypeScript. Because we're gonna use sort of eager values, like immediate values like that, and lazy values wrapped in a function a lot and interchangeably throughout the examples. And without TypeScript, I have no idea how I will be able to actually properly show all of that. Like, because it's so easy in JavaScript to make a mistake and forget to wrap it something into a function. What's interesting is that in Haskell, you may think of the whole language where every type is wrapped into such function automatically. It's everywhere. That's why you never have to actually explicitly say that. So the Haskell will automatically wrap everything into a function and call that function when needed. But I'm pretty sure it's not implemented in terms of functions. It has probably some kind of more efficient way of representing all of that, but you can think of it like that to make it a little bit easier for yourself. Okay, and to actually call these things, you have to wrap them like that, and then the result of this function also has to be called. And there we go. Here is the eager sum, and here is the lazy sum. I think it would be actually pretty great to mark them somehow, to label them somehow. So this is eager sum, and this is going to be lazy sum. Okay, so this is basically how lazy evaluation feels like in Haskell, in languages like Haskell. So in this particular situation, 10 plus 5 is not going to be computed outside of the function. It's going to be computed inside of the function exactly when it's needed. The question is, why the hell would you need something like that? Why would you want to program in a style where everything is sort of wrapped in a function and postponed until it's actually needed? What's the benefit of this kind of style of development? Like, why would you do that? And even on top of that, create a whole language that, that enforces this kind of style. So, interesting thing, you don't evaluate something that you don't need. So, if you have a big operation, a very heavy operation that you're never gonna need, it's never gonna be calculated. So you may have, in some situation, performance benefits. How about that? So, okay, to make our life a little bit easier, let's actually introduce a new type that represents the lazy type. In TypeScript, if I remember correctly, you can introduce type synonyms or type aliases. I don't even know how they're called. And on top of that, the alias can be generic. And generics work very similarly to Java generics. So yeah, they got the idea from all sorts of different languages. So what you can do, you can define a type lazy t and make it equal to function that doesn't take any argument and returns t. So after that, it should be quite easy to do something like a boom, boom, and as you can see, so now at the type level, we can clearly see when a value is lazy and when it is not lazy. So it's a little bit easier to read it like that, I think, in my opinion. So we explicitly marking a value as lazy. Yeah, and everything seems to be okay. So let's actually take a look at the example when you can avoid a pretty heavy computation using lazy evaluation. So the famous example, I think, is something along the line. So let me actually type some kind of like a separator here. This was some sort of introduction. And here's avoiding big computations that are not needed. All right. So imagine that you have not only a big computation, but the computation that never actually ends. So something, for example, like hang. right? So hang function, believe it or not, hangs. So, and to make it applicable to any kind of type, we're gonna make it generic, right? So it always returns t, so you can assign it to any type. And once you will try to compute this kind of function, it will hang immediately. And consider the following function. Let's call it first. It takes two arguments, a and b, and returns. Guess which one it returns? It returns the first one, right? It returns the first one. So if you assign something like 10 hang, what will this function return? Let's find out. Well, it didn't really hang, but it actually exceeded its, the stack limit. So we could have actually put some kind of like an infinite loop there inside of a function, but I just decided to go with the recursion because we're sort of developing everything in a functional style. That's why I'm using the recursion a lot. But anyway, but what if the function first was lazy, right? What if it used lazy type? Let's find out. Let's introduce a lazy first. And this one is going to be lazy. This one going to be lazy, and the result is also going to be lazy, right? And I'm going to use a lazy first. If you try to run something like that, it will tell you that you forgot to wrap this thing in a function to actually make it lazy. You see how TypeScript actually helps us to find errors. Yes. Static typing, by the way, no, it does not limit your creativity. No, it does not force you type redundant things. It helps you. It helps you. Okay, and let's put something like lazy first. There we go. And what's funny is that this is where it didn't really help us, because console log is a very dynamic function that basically inherits its behavior from JavaScript. Yeah, but at least we can see the error here in the output, and we can actually force it. So yeah, it returned 10 despite having an infinite computation in one of its parameters, but since we never used that parameter, it never actually hang. What is the past of hang? I don't know, but you get the idea. Hanged. Regular verbs. Who needs them? Hung. Okay, thank you. And how would something like that work in Haskell, for example? As I already said, in Haskell, everything is lazy automatically. You don't have to do any of this stuff. It's by default lazy. If you open GHCI, and you define a function first, like it takes a and b and returns a. So if you do something like that, it will return you 10. So, and you can also define function hang. It's actually super easy to define. You make it equal to itself, and then when you run it, it hangs. It just hangs until you Control-C it. And if you do something like 10 hang, it will be still there, but if you swap the arguments here, if you put hang as the first, at 10 as the second, it will never finish. Because now you put the infinite computation to the argument where it's actually needed, and it hang. So you see in Haskell, it's automatically like that. The language is lazy by default always. But here in TypeScript, we always have to mark it like that. Anyway, so cool. You can avoid big computations. What else? Well, something like short-circuit evaluation, it's called in other languages, not functional, not lazy languages, it's called short-circuit evaluation, happens naturally. What is short-circuit evaluation or computation? I don't exactly remember what's the last part of it. Who knows what it is? What is short-circuit evaluation or short-circuit computation? Short-circuit computation. I think it's evaluation, see? When it does evaluate the right side of the expression, it doesn't matter. Yes, it is related to Boolean operations. And let's actually Google that. Short circuit evaluation, or maybe computation, I don't know. Help me out, DuckDuckGo. Oh, yeah, I was right. It's evaluation. Would you look at that? Would you look at that? So, yeah, the idea is take a look at AND operation. Right, take a look at AND operation. If first operand of AND is false, it doesn't matter what's the second one. It just doesn't matter because the whole result is going to be false anyway, and the second argument is never evaluated. So what's funny is that in majority of the modern languages is if the right expression has side effects, they also will be not happening.
Haskell rank is coming back.
I have no idea. I kind of, they kind of start feeling repetitive, so I stopped doing them. So maybe I just need to find like a difficult and interesting task, and maybe then I can make another episode. I'll think about it. Thank you for bringing it up. So yeah, it's very close to lazy evaluation, as you can see. It's very close to lazy evaluation. It just has a different name. It's almost like in in computer science, people are inventing the same thing in parallel, independent of each other, like anywhere else, I guess. So in lazy evaluated language, that thing happens naturally. Let's find out how. So let's define a function and it takes two arguments, a and b, and all of them are lazy booleans. All of them are lazy booleans. So how would you implement something like that? Without using this operator, by the way. So to make it, the actual implementation, we should not use this thing because, I mean, it's already implemented, so it's cheating. Basically, we're gonna do if A is false, well, it's always false. It doesn't matter what B is. If it's not false, well, that means the result of the whole expression is going to be B, because it will just depend on B. If B is false, then the whole thing is false. If it's true, and A is true, well, that means everything is true. And on top of that, we have to return this thing as lazy. Can you already see why this function will have short-circuit evaluation behavior? Because if this thing is false, we're gonna fall inside of this branch and we'll never even call B. Let's actually try to test this assumption and see if it's true or not. Let's do like a truth table for our function. So we're gonna have 4 parameters, I think: false, false, true, false, true, true, and false, true. So what we're gonna do here, we're gonna use a little bit of Emacs magic by wrapping these things in functions, making them lazy. As you can see, Emacs is very very stable in that sense. And then once we called them on these parameters, we have to evaluate those things. Emacs. And let's actually print all of that. So we're going to use console log. I'm going to put this thing here, replace this thing with this kind of stuff, not this one, but rather this one, equal, boom. So let's verify that this conjunction works correctly. Let's verify that. So I'd also like to separate, this particular output from the rest of the output, so it's a little bit easier for us to read. Yeah, why not? Let's use equals. Okay. Okay. Boom. So, is it correct? Okay. It is only true when both of the arguments are true. If any of them is false, the whole thing is false. Okay. But how can we know that the second argument is never evaluated when the first one is false? How can we verify that experimentally? Is there any way to verify that experimentally? We can do that with logging. So let's introduce a very interesting function called trace. It's a generic function and it takes a lazy generic value and returns another lazy generic value. It acts like ID. Basically, it doesn't modify the value, it just returns that value. But on top of that value, it's also going to take a message, not lazy one though, that it's going to print when somebody will try to evaluate that value. How would you implement such thing? Well, you would wrap this value into another function that will perform the logging of that specific message. Let's quickly do that. So here's the function, here's the outer function. Inside of that function, we're logging that message, and only then we're forcing this lazy value. So you see, the result is still a lazy value, but once you try to force that lazy value, it will perform the side effect. Does it make any sense? Oh, it does. So how are we going to apply all of that here? Let's find out. So I'm going to use Emacs magic yet again, and I'm going to wrap this value with trace. And what kind of message I want to print there? Well, since it's a left argument, I'm going to put L there. Okay. It probably was a bad idea to actually get rid of the multiple cursors right now. And here, we're going to do a very similar thing, but we're going to put right here. All right. And I think it makes sense to actually format it slightly, like that. So, if function add and will touch any of its argument, they will scream with this message, and we will clearly see whether it touched left or right value. Let's find out if it's true or not. Okay, something interesting is going on. So you see, for false and false, it only touched the left value, but it never touched the right one. For true and false, it touched the left value, it figured out that the left value is true, and we need to check the right one. So, yeah, it checked the right one. The same for this one. And of course, since the first one is false, it doesn't matter if the second one is true. It just doesn't matter. Everything is false, and we never touched the right one. So you see, once you mark all of your types as lazy, the short circuit behavior happens naturally, and this is not something that you have to hard code into your language. So something like that. So this is sort of like the second benefit of a lazy evaluation. Something just happened naturally. Not the biggest, benefit, but anyway. The same goes for disjunction as well. So we can even, to make it complete, let's implement OR, right? How would you implement OR? What's funny is that OR is kind of an opposite. If A is true, it doesn't matter what is B, the result is true. If A is false, it will depend on B. So this is basically the disjunction behavior. And we can try to verify that. I'm going to put a console log. Something, let's actually put 3 of them. And let's copy paste this thing here. So what I'm going to do, I'm going to go ahead and replace this thing with double bar. I'm going to replace AND with OR, and I'm going to leave this the code everywhere else the same. Okay, there we go. And here is our disjunction. You see, when it became false, it needs to check the second one, because if the second one is going to be true, the whole expression is going to be true. So the first one is true, doesn't matter what's the second one, everything is true. The first one is true, doesn't matter what the second one, it's true. Second one false, first one false, but the second one is true, the whole thing is true. So you see, we can clearly see what arguments were checked. Everything works as expected. What would be another benefit that we're going to take a look today? I guess the main and the biggest benefit that everybody is talking about when they talk about lazy evaluation, and I already saw somebody screaming about it in the chat. Yes, we're going to talk about the infinite data structures. Infinite data structures. Can you imagine that? How can you hold an infinite data structure in the memory? How can you do that? But you can. So some parts of the data structure are not evaluated yet. That's why you can have infinite data structures. Let's take a look at the simplest one, lazy list, linked list, everyone's favorite. Anyways, so how would you define a lazy list in TypeScript with the lazy T type? Okay, infinite data structures. Infinite data structures. Interestingly enough, in TypeScript you have a very epic feature where you can define type aliases like so. You can define a type foo that is number or string. I guess you can think of them as union types. Maybe they even called union types in terms of a TypeScript. But anyway, and if you use foo, the compiler will check whether the type you're trying to put there is either number or string, which is pretty convenient. As a matter of fact, the type system of TypeScript is extremely powerful. It's very powerful, and I think this is exactly what you need to, control the wild language like JavaScript. I guess you need a very powerful type system to actually hold the whole JavaScript in place. So that's why it's so powerful. Anyway, we're going to use this kind of thing to implement a sort of algebraic data type thing. If people who program in Haskell, they probably know what I'm talking about. Let's introduce a thing called a lazy list. A lazy list. Lazy list. So what is a lazy list? What is a lazy list? Well, empty lazy list. Let's denote an empty lazy list as null. Null, by the way, is a type as well. There is, as far as I can tell, there's such type in, or maybe not. Because I just remember that in TypeScript you can even define types that look like this. I think you can do something like that. So basically you define a new type as enumeration of specific values, and yeah, if you don't put that exact value there, it's going to be a compile time error. So I guess in this particular situation this is not really a type, it's rather a specific value. Yeah, but I'm going to use null instead of undefined because I think it's a little bit closer to what I'm trying to achieve there. It's a little bit closer to what I'm trying to achieve there. Anyway, so it's going to be either null or a pair of values. As far as I can remember, again, in TypeScript, you can actually define your own structures by just writing them as a JavaScript object. So the first element of the lazy list is going to be the head. Maybe I'm going to even call it the head, which is the lazy value of t. And the tail is going to be the rest of the lazy list, the rest of the elements of the lazy list. And on top of that, the whole list also should be lazy, like so. So this is how you would define such type. Since this entire thing is a type, you can put it as a type parameter for lazy value. Let's see if it works. Let's see if it works. How do you like this type definition? That's why in Haskell, everything is lazy automatically, and you don't have to explicitly mark anything as lazy because you don't have to deal with this kind of nonsense, but it is what it is. Let's actually find out if it compiles or not. I have no idea if it compiles or not. Well, it does compile. It does seem to be compiled. It's kind of inconvenient to, work with this type. Maybe we can introduce a function that takes a regular array and generates you a lazy list. That will be actually pretty convenient, I think. Let's actually quickly do that. Let's call it toList. It will take array of course, it's going to be, like a generic thingy. How do you define arrays? Is it just number this? I think this is how you do that. And it will return you a lazy list T, right? Lazy list T. So, as far as I know, you cannot even return null. Lazy list is lazy all the way through. No, it actually worked surprisingly enough because... Oh, I guess it made null... Okay, sure. Oh, yeah, T. Thank you, Supercuber. It's kind of strange. I don't quite understand why it doesn't complain on putting null there. I guess it nulls the function. Yes, it nulls the function itself. That's probably why it's doing that. But if I wrap it with a function like that, it's also not going to complain about this anyway. All right, so how can you convert an array into a lazy list? It should be fairly straightforward. If access is empty, how do you check the length of the array in JavaScript? I don't remember. I think it's just .length, and then you check if it's 0 or not. If it's 0, we're going to return null, right? We're going to return null. Otherwise, if it's not 0, we're going to return a pair where the head is equal access 0 and tail is going to be equal recursively to list and a slice of access without the first argument, but I don't remember how to do that in JavaScript. Do you guys remember how to do that in JavaScript? There was a function like slice that takes an array, and I think it takes the first element there and it will just work. Oh yeah, it's x slice 1. Okay, thank you, evolve your mind. I guess this is how we do that. Like it's very similar to slice syntax like in Python, but they decided not to embed that into the core of the language, so it's a library function. So yeah, this is basically how it's gonna look like essentially. All right, let's try to compile that and see if we didn't make any mistakes. We apparently did some mistakes, which is very interesting. Yes, this thing has to be lazy. Forgot about that. This thing has to be lazy. There you go, it compiled, and let's try to print it and see what exactly it will print. So console log toList 1, 2, 3. 1, 2, 3. So, and we get a function because it's a lazy value. And if you remember correctly, lazy value is basically a function. But what's going to happen when you try to call this function? What's going to happen when you try to call this function? Well, it returned you a pair where head is a function and tail is a function. Okay, let's try to take head and call it and see what's going to be there. All right, it was 1. So if we try to do the same, but instead of head, we're going to call it tail. Well, it's the next pair. It's the next pair. So we sort of like unwinding that lazy list one by one, like layers of onion. Yeah, because that's exactly what's happening here. Because here we recursively build that onion, and now here we manually peel it back. What if we call head of that tail? So what's going to happen? Now we have the second element, 2. Okay, What if we put another tail here? The next value. Will we receive the next value? Here you go. It's 3. Next, will we receive the next value if we try to call it like that? And we won't. Why? Because, yeah, head turned out to be null. So if you take a look, if you remove this head from here, the last element was null and it indicates the end of the list. We cannot go any further. So it's a really weird thing, but it's still finite structure. How can you implement something like that but infinite? What if we could make this list that infinitely goes to infinity? Like you will never encounter null whatsoever. Let's try to do that. Let's implement a function called, how would I call it? Range. It's going to take a number from what number is going to begin, and it will return you a lazy list of numbers. So how would you implement something like that? All right, let's take a look. You simply return head begin, because begin is already lazy, so we can just put it here. And what's going to be the tail? Tail is essentially going to be a range where begin +1. So we recursively generate an infinite list, but it's never gonna Stack Overflow, because it will evaluate the next element only when you try to access it. That's the thing. So it only evaluates this element when we actually try to access them. It's never evaluated until it's needed. Never evaluated until it's needed. And all of that actually very close to generators in Python, or maybe there are generators in JavaScript these days. So as you can see, lazy evaluation gets to the mainstream languages these days quite quickly. As a matter of fact, a lot of functional programming ideas, they never made functional programming languages successful themselves, but the ideas sort of soaked up into mainstream languages, and now we kind of have them in a different form, in a different name, but we still do have them, and they're useful. They're useful. So, all right. So let's try to do the following thing. I'm gonna do console log range. Let's start from 3, and let's see what's gonna happen. So I'm gonna actually separate whatever I'm doing here. Console log 3, and let's see what's gonna happen. Okay, doesn't compile because this thing has to be lazy. All right, so function, obviously, excuse me, you have to force this thing. All right, so now it's a pair. If we take a head of this thing, it's 3, because we instructed the arrange function to start from 3. Oh, already JavaScript has iterators and generators. Okay, very well then. So maybe my entire talk is actually obsolete, but I still want to show how it feels like in Haskell at least. So, and let's repeat the same procedure. Okay, tail 4. Yet another tail. Copy paste it like that. 5. 6. 7. And it will never end. It will just never end at all. So since it's not really convenient to, peel off these lazy lists like that, let's implement a function that prints lazy lists for us. That will be way more convenient. What do you guys think? I think it's a good idea. Let's implement that. Let's implement that. So let's implement a function called print list. It is going to take a lazy list I guess of t, because we can just pass t to the console log, and console log can print pretty much anything. So let's actually make it generic. And I guess this function is not supposed to return anything. It is not supposed to return anything. Okay. I guess we'll have to maintain the current pair all the time, because you see, access is a function. So before even checking whether it's null or not, I have to force it. Right? After I forced it, I can check whether pair is null or not. Is that the idiomatic way of checking whether something is null or not? I don't quite remember. Yeah, and of course it has to be not equal. Of course it has to be not equal. Yeah, if it's not null, what do? We just console log pair head, forcing the head, by the way, and then assigning pair tail to this thing. So you see, we automated this step here with a while loop, right? So, and let's test if it works or not. So first we're gonna print just a regular finite list, just to verify that it, generally works, because maybe it doesn't work at all. Maybe it doesn't work at all. Would you look at that? It did work for a finite list, but what about infinite list? What's gonna happen if you try to print an infinite list? What's gonna happen, chat? Is it gonna blow up? I have no idea. It's actually kind of scary. Imagine printing an infinite data structure. Have a go. Of course, 3 also has to be infinite. 3 also has to be infinite. Well, it went for a while, and would you look at that? What the hell is that? What? Print does not even do any recursion, and it's still got Stack Overflow. What the hell? Well, the problem is not really in print list. The problem in the range implementation. The problem is in the range implementation. Let's take a look at it. So, can anybody spot a problem? Can anybody spot a problem? We take begin as a lazy value, and we put that lazy value without even forcing it. So you see, to construct a lazy list, we're constructing a lazy list of lazy values that are never evaluated unless you try to touch them. Right? So that begin, if you put a very heavy computation into begin, it will never be evaluated even if you try to traverse the list, because that traversing doesn't even try to touch it unless you go to the second element where you are trying to touch it. So what you ended up here is a very interesting situation where you have first element equal to function that returns 3. Second element, as you can see, we put this expression as a second value, right? Second value is gonna be ended up with a function that looks like that, where begin is the previous function. So you basically replace begin with this function. Then you can just repeat that process infinitely, where you basically take the previous value and replace it, replace begin with it. You see where I'm going? You see where I'm going with that? So this is basically the process that we have here. What you end up with is a growing postponed computation. You ended up with the list with a growing postponed computation. And this is one of the downsides of lazy evaluation. You have to know how it happens, because you can end up with something that you can classify as a memory leak. Yes. So, and this will grow, and that actually contributes to the Stack Overflow that we witnessed here. So, lazy evaluation actually solves one class of the problems, but introduce another one. So it has pros and cons. So when you work with lazy evaluation, you have to keep these things in mind all the time. So how can we mitigate this thing? How can we mitigate this thing? Well, we can just go ahead and force begin. If lazy list is already lazy, why head is lazy too? Why not make head not lazy? It's a good question. The reason is I wanted to demonstrate the true experience of Haskell. Not sugar-coated, but exactly the problems that you have to deal with when you program in Haskell. So because Haskell is not an ideal language and there are problems there, quite serious ones, that are difficult to solve, and here they are. Everything is lazy, and here's the consequences. And you have to deal with these consequences. So in Haskell, this particular range would not be as bad as in TypeScript because of separate small details, but still, there are similar problems in Haskell. Okay, so in this particular situation, we can just force begin like that. And it will pass, yeah, and it will just go indefinitely. It's even faster. Can you notice it reached 17K faster? Like, because we had a problem on 17K. Let's actually go back to the original implementation. So it blows up at 17K. Okay, it blew up at 17K. But look at the speed with which it actually reached 17K. It was actually quite slow, but once we start forcing this thing, right? Yep. Once we start forcing this thing, semicolon, is that semicolon? What small stupid mistake did I make? What small stupid mistake did I make, chat? Head should be lazy. Thank you. Yes. That's exactly why we're using TypeScript. It already reached 17K. It already reached it, and it actually went beyond it. So, lazy evaluation does make some things faster in very specific situation. But in some situations, it can make it even slower. So there are pros and cons. This approach is not ideal. This approach is not a silver bullet. Keep that in mind all the time. It's just a different approach. This approach is not a silver bullet. No matter what, Haskell fanatics tell you. Because they will tell you all sorts of crazy shit. Seriously, they will tell you everything just to convince you that this is like the solution to all of your problems. No, this is not. This is simply a different approach. And let's just keep it that way. It's simply a different approach. Anyways, so, all right. So there's a print list and there is a range. What kind of advantage do you have with infinite data structures? What kind of advantages do you have with the infinite data structure? Well, you can take a substructure of the infinite data structure that is finite, and your program still will be terminated. Right? Infinite data structure, finite subset of it, small p finite piece of infinite data structure, and your whole program is actually terminating. This is the things you can do. For example, we can implement a function that takes n elements from the infinite list, and it will still terminate. Let's try to do that. This is actually a pretty common function in Haskell. For example, if you have an infinite list, here's an infinite list in Haskell, your encoding is probably terrible, but it is what it is. This is how you know H264 encoding usually deals with a lot of moving small characters, and I really apologize for that. So imagine that you have an infinite list and you can take 10 elements of it, and here you go, our program terminated. We took a small finite subset of the infinite data structure and the program still terminated. This is what you can do with lazy evaluation. How can we implement something like that? Let's just go ahead and implement that. How about that? Let's just go ahead and implement that. Function take. So it is going to take n number and lazy list t and return another lazy list t. All right, there we go. There we go. Let's return a lazy value. Again, let's first force n to not repeat the mistake of range. Let m n force. Next, we check if m is 0. If m is 0, well, there's nothing to take. The caller of this function is literally asks us to take 0 elements out of the list. So we need to return an empty list. How do you return an empty list? Well, empty list is just null. That's what it is. It's just an empty list. Next, if m is greater than 0, well, it would be better to actually swap the branches and make this thing like that. I guess it would be a little bit more correct, just in case m happened to be negative, which it shouldn't be, but we all know how it ends up at the end of the day. If something can happen, it will happen, no matter how hard you try. So let's actually help ourselves. Okay, and what we're doing essentially, we are assigning head to the head of the access list, and tail is take m-1 from the tail of that list. So you see, we're sort of crawling on the list, decreasing the counter, and once the counter has decreased, we just chop the tail and just return that finite list. And since the tail is lazy, it's never evaluated, so it will be just dropped off. And no matter how big it is, no matter how many computations you have in that tail, it will, you know, still not happen. Don't forget to return a lazy. I wrapped the whole thing into lazy. Yes, I wrapped the whole thing into lazy, so don't even worry about it. Yeah, this is something that you can also do. Okay, so right now, again, this is an infinite computation. Nah, the problem is not that, like, this thing has to be lazy as well. Yes, this thing has to be lazy. See, this is why we're using TypeScript. Imagine if I didn't use TypeScript and try to do something like that in JavaScript. That would be nightmare to actually troubleshoot, because it will try to compute that and do all sorts of random things. Maybe not. Maybe it will say, number is not a function. Why are you trying to call function? And I would have no idea what exactly is going on, where exactly I have to make fix. This thing is also not helpful, so maybe my arguments are not that appealing anyway. So okay, what did I miss here? What did I miss? I know what I missed. I never forced access. That's right, I never forced access. But I don't really want to force it 2 times, so let's actually force it and sort of remember it like we did in the print list, right? And we're gonna replace this thing with pair like so. Yeah. In Haskell, it's way simpler. Yeah, you see, it's still infinite as it's supposed to be, because we never actually try to do take. And let's take 10 elements out of the infinite list and see if it will actually happen. again. Is it really 10 elements starting from 3? Yes, it's 10 elements. Would you look at that? We took 10 elements out of infinite data structure. Out of infinite data structure. How about that? How about that? Isn't that cool? I think it's pretty cool. I think it's pretty cool. So another interesting operation that is very helpful in working with infinite lazy lists is filtering. And you will see a lot of Haskell using that filter function all the time. For example, one of the things you can do is take an infinite list. It's an infinite list. Yes, enjoy your encoding problems. You filter only even numbers out of infinite list. So you cannot see that probably. You can't see that, but these are only even numbers. Yes, these are only even numbers. And then once you generated an infinite list of even numbers, you can take 10 of them. And here you go, you generated 10 even numbers. So this is basically what people do in Haskell. They generate infinite data structure, they filter infinite data structure, and they take small subsets, small finite subset of an infinite data structure. So this is like a sort of a different way of thinking about programming, like different way, not the best way, not a silver bullet, just a different way. Keep that in mind. It's just a different way. So don't let Haskellers to rope you into their cult. It's just a different way of thinking about programming. Don't let them do that. Anyways. So let's implement a filter. Let's implement filter. Too late. Anyway, so yeah, for some people it might be too late. So for an ultimate Haskell experience, a filter takes a function, right? Filter takes a function. That function takes the element and returns a boolean, and that boolean tells that function whether to keep the element or filter it out. For an ultimate Haskell experience, you have to make this argument lazy. The result also has to be lazy, and the function itself has to be lazy. You know, it's for ultimate Haskell experience, right? But do we really want to go that route? I guess for educational example, I'm just going to mention that in Haskell, it's going to be like that. But we're going to keep it, you know, strict. It's not gonna affect our example in any case. But it's quite important to keep in mind that in Haskell, it's probably going to be like that. So if I can get away with this kind of thing without affecting the example that I'm gonna show, I think I'm gonna go that road. Anyway, so lazy list t, and this thing is going to return a lazy list t. So how can we implement that function? Similarly to take, believe it or not, similarly to take. So we return the lazy value. I suppose I'll have to pre-force access. And I need to check whether access is empty list or not, because if it's already empty, there is nothing to filter anymore, and I just have to return an empty list. So if pair is null, you can't filter an empty list. There's nothing to filter an empty list, you return an empty list. Otherwise, what do? You check that the head actually is something that we want to keep. So we take the first element, the head of the list, we put it into the predicate. So yeah, I just remember the the name of this function. It's a predicate. Yes, function that takes an element and returns a boolean is called predicate. And if it is the predicate that I'm thinking about, it might make sense to also pre-force the head like so. And in that particular situation, we're gonna return the pair where head is X and the tail is filtered tail. Yes, the tail is filtered tail. So we pass F on and we try to filter the tail of it. Okay, if the element is not something that we want to keep, we're gonna return just the tail. So we see we're dropping that element. We're just dropping it. Yes, this is basically what we do. Yeah, if the list is empty, there is nothing to filter, it's empty list. If the head is compliant with the predicate, we keep it by constructing a new pair and giving the tail a filtered tail. So it's going to continue recursively doing this thing. If X is not something that we want to keep, we just return a filtered tailed, effectively dropping the head. And I guess that's pretty much it. That's pretty much the implementation of a filter that is not probably going to compile the first try. Let's find out. Of course it didn't. Property tail does not exist on type. Oh yeah, of course. It has to be pair. Sure. This is why I'm using TypeScript, because I'm constantly making mistakes like that. Or maybe this is because I'm just stupid. That might be the case. No argument access was provided. 151. I guess, yes, modality. I think you're right. I think I forgot to, yeah, I completely forgot the TypeScript syntax. Keep in mind that I'm not a TypeScript developer, so I may not know a lot of things there. There we go. Even crazier compilation error. I'm just realizing that my arguments for static typing are not looking very appealing. Okay, sure. Yes, we don't need static typing. You see, this is what static typing leads you to, right? Unreadable errors. If it failed at runtime, it would be more clear what exactly happened. Am I right? That's exact. Yes. Why do you need static typing? Why do you need static typing anyway? 52. Oh god. Actually worse than Haskell errors, exactly. So it's even better than, you know, ultimate Haskell experience. We wanted ultimate Haskell experience. Here it is. Here's the ultimate Haskell experience. Okay, anyway, 152. Let's go back. So this is where it complains. It says that it's not a lazy list, but if we return null, okay, this is where we return this. You see, we already wrapped everything into lazy values. So the values that we return in these 3 exit points, yes, I have 3 exit points out of the function. Please don't tell the extra. So this has to be not lazy values, but the result of filter is lazy, and that's why I have to force it. There we go. So at least it compiled. Let's try to filter infinite list with this filter function. Yes. So let's actually put console log 3. Let's generate an infinite list starting from 1. Let's filter even numbers. So how can you determine whether x is even or not? Well, you divide it by 2, and if it's equal to 0, that means it's even, and we want to keep it in the final list. And then we're going to try to print that list. Oh, would you look at that? Emacs has finally managed to start up TypeScript server, and it actually tries to help me by twitching at the bottom of it. Yes, Emacs thinks that this is helpful. Yes. Emacs thinks that this is actually helpful. Anyway, let's actually try to run it and see. And of course, ultimate Haskell experience. Ultimate Haskell experience. Forgot about this one. All right, so it's doing its thing. And these are even numbers, as you can see. These are even numbers. Let's try to take a small finite subset out of the infinite list of even numbers. Take 10. This probably has to be, lazy. Like that. And let's just run it. Would you look at that? Now we have 10 even numbers that we took out of infinite list of even numbers. So yeah, that's just an alternative way of thinking of of programming. Not the best way, just an alternative. Okay, maybe you want to even sort of. Now this feels like Lisp, I guess. It does feel like Lisp. Okay, all of that is cool and all, but how can you make it useful? Well, this kind of approach makes it difficult to compute prime numbers using, how is that called? My English is so bad. Sieve of errors? Okay, let's Google that. Yeah, that does not make it easier to read. Yeah, this particular approach makes implementing this thing easier. I'm going to show you how. How many of you know this approach? Let me try to pronounce it. Eratosthenes. Eratosthenes. I hope I pronounced it correctly. Yes. Okay, so this is the visualization of the approach. What you do, you take infinite list of numbers. You see, it's already actually fits to our model. You say that 2 is a prime number, and then you remove everything from that list that is divisible by 2. You take the next element. You say it's a prime number, and then you remove everything from the list that is divisible by 3. And you do that indefinitely. You see how it fits perfectly to our model of infinite data structure, infinite lists and operations on them, like take and filter and so on and so forth. It fits actually perfectly. As a matter of fact, the idea of implementing this algorithm for this particular stream, I got from the computer file video about Haskell. I think it was called To the Infinity and Beyond. So I'm going to leave the link to this video in the description, and also I'm going to put it in the chat if you're interested. So let me find out computer file To the Infinity, I think. Yeah, To the Infinity and Beyond. So I really recommend you to take a look at that specific video where they implemented that exact example, but in Haskell. So I'm not going to implement it in Haskell. Instead, you can just watch this video. But we're going to implement that example in TypeScript, but in a similar style. That's right. Let's try to do that. Let's try to do that. All right. So we need a function. I guess I want to find my separator here. Here it is. Yeah, well, we're doing lazy sieve, yes. So we're going to have a function sieve that takes lazy list of numbers and returns a lazy list of numbers. So we need to know what exactly it does. It will take the head of the list and filter out everything in the tail that is divisible by the head. And it's going to do that recursively. Yes. Take the head, take the tail, filter tail, filter out everything that is divisible by head, and do that recursively and sieve again. This is how we're going to do that. I really recommend to watch the computer file video because they also have visualizations of that process, so it might be helpful to understand. All right, so let's actually quickly do that. First of all, we're going to force the access. Here's the pairs. And there's nothing to sieve if pair is null. So we're going to say if pair is null, well, sorry, there's nothing to sieve. I really hope I pronounce it correctly. Anyway, if it's not null, what do? We take the tail and we filter it, and we need to filter out everything that is divisible by the head. But we need to force the head first. So here's the pair head. So we force the head, we have the head. X is the element from the tail. So we take X mod Y equal 0. So, but we need to filter out everything that is divisible by head. So we're gonna put inversion here. So yeah, so the tail is properly filtered out, and what we're gonna do with that tail, we're gonna sieve it again. So you see, it's gonna recursively take the head, filter, sieve. And that sieve is going to take the head of the filtered thingy and going to filter again and sieve, filter again and sieve. And by that, it will generate a list of prime numbers, because only prime numbers will survive this very intensive process of sieving. Yes, because they are not divisible by anything but themselves. Yeah, pretty much the idea. And of course, here we're gonna just return that. And look at the entire implementation. This is basically it, surprisingly. And let's introduce a variable called prime. And prime numbers are gonna be simply sieve range 2. Range 2 generates an infinite list from 2 to infinity, and then we sieve it, which will make 2 the first prime number, and starting from that, it will, it will generate prime numbers. Okay, and let's try to take 10 elements out of prime numbers list and print them, and see if it will actually generate 10 prime numbers. Will it do that, or will it fail? Well, it probably will generate an unreadable compilation error. Yes, I was right. Well, it was readable at least, because I know exactly what's going on. I forgot about ultimate Haskell experience. Yes, here's the ultimate Haskell experience. Yes, now we're going into the realm of unreadable errors. Nice. So it's kind of similar. I think I forgot like semicolon somewhere here. No, it was not a semicolon. Let's think about again. This value has to be not lazy. That's why we have to force this thing here. Yes, I think. All right. And it didn't generate anything. Nice. Even though we explicitly asked it to... Oh, because it... Oh, okay. Okay. I guess we screwed up somewhere. Here's the lazy value. I force the pair. If it's empty list. Okay. I force the head, and I use the head to filter out the list. But you know what I forgot? I forgot to keep the head. Yes, I just dropped the head. I'm using the head, but I just dropped it. I just dropped it. So that means I need to continue generating the list. So head has to be put back in place, and the tail is going to be this sieve. And that does not require forcing that sieve. Yes. That's where I made a mistake. Can it generate 10 prime numbers now? It can. In fact, it did. Are those prime numbers? Does this list of 10 numbers contain a non-prime numbers? Anybody tell me? I think it does contain only prime numbers. But what if we remove take? If we remove take, it should keep generating prime numbers, because prime is an infinite list of prime numbers, which is lazy. That's why it can be infinite. Let's find out. So it keeps generating something, and notice how I think it slows down over time. I think it slows down. Let's actually take a random number from here and check is prime. Oh, nice. Thank you, Amazon. Very cool. Okay. Check if number is prime online. You know what? I think there should be way easier way to check if it's prime or not. If I remember correctly, Linux and Unix operating system have a very interesting function called factor. I bet you didn't know that, but there is a function called factor that factorizes your number. And if you give it, yes, I know, you didn't know that. I didn't, like, it's so underrated program. If you put a prime number there, yes, this is the only factor of prime number itself. There you go. So yeah, we just proved that a random number from our generated list is a prime number. So yeah, this is how basically you can think in terms of lazy evaluation. And this is basically how you have to turn your thinking inside out when you program in Haskell. Again, this is not a silver bullet. It's just an alternative way of programming. A very interesting one, I have to admit, a very interesting one.